Writing basic queries. In order to become a SQL ninja, we need to understand all the different parts of the select statement. So we'll start by refreshing what the select statement is all about. We'll break it down piece by piece. All the clauses we'll look at: select, from, where, order by, group by, having. We'll take a big look at all of them, see how they work, and write some queries that utilize them. Then we'll take a big look at joins. Joins is certainly one of the more difficult parts to grasp when it comes to learning SQL, so we'll take a good look at all the different kinds of joins and give some good examples along the way. Let's jump in. Let's start with a quick review of the select statement. Remember, select, by far the most popular SQL statement out there. It's what we use to query databases and to read data out of the tables. We always begin our statement with the select clause, and then we specify what column or columns we want to pull out from the tables that we're querying. And remember, an asterisk or a star is a shortcut for give me all columns from our table. So in this case, we're doing an asterisk, which means give me all the columns from this table. From is what table or view we're pulling those columns out of. So here I actually made a view called track details. I'll show you this view when we get into the virtual Nugget Lab. And that is what we're reading from. So we're saying give us all columns from this view, which, by the way, has 5 or so tables underneath it that it's pulling from. Where is our filter? So this is how we are going to filter specific rows out of the table. And then order by is what we use to sort by a specific column. In this case, we're actually sorting by 2 columns. We're sorting by album and then by track. So each one of these will be sorted within their specific album. Let's head over to the Virtual Nugget Lab and write some basic select statements. Welcome back to the Virtual Nugget Lab. Let's bring up SQL Server Management Studio. I have a connection to our local SQL Server 2014 instance here called SQL Nugget. We've got a couple of databases on here, and we're going to be working in our project 08 writing basic queries. Now, if you want to follow along or try this out in the Virtual Nugget Lab on your own, and you want to get to the exact state that we are here, you can open up setup.sql and run the script. If you already have databases on there, don't worry. It'll drop them, recreate them, reload them up with data, and get to the exact point that I am here. So I'm going to go ahead and do that anyway, and that's just going to take a second to drop those databases, recreate them, recreate all the tables, and then reload them all with data. Perfect. And now I've also got a view here. So execute this as well to create the view. Now, the reason I created a view is because our MusicDB is a very well-designed, highly normalized database. And what that basically means is we have lots of small focused tables, which means even our simple queries, when we need to pull data from multiple tables, are going to require joins. So queries are going to get complex quick. And in order to learn the basics, I wanted just one big table. So that's what this view really is. It's one big table that pulls all the relevant information out of all of these tables. And that's the whole purpose of a view, is to simplify the underlying schema. So when you have power users out there or developers out there that need to utilize the data, generally what you'll do is wrap all that complexity into a view and make it look like one big simple table, and their queries will then be simple to work with. So that's exactly what we did here. Just wrap all of this complexity inside of a view, and we'll come back to this once we learn how joins work. All right, so we've got that view created. You can actually see it here in the database if you expand views, and you can see a view is really just a virtual table, right? It's a stored query. So we can execute queries against views just like you would against tables. All right, let's close out of our view here, and let's open up our first script full of lots of queries to learn the basics of select, order by, and where. So the simplest possible query to write is this: select everything from table or view. So select star, meaning give me all the columns from our table, or in this case our view, track details. And if we execute this, here it is. Here is all of that data. And remember, this is track detail, so our level of granularity here is down at the track level. So we're going to get a record for every single track in the track table. And here it is. Here's the artist, the album, the track, the genre, the media type, milliseconds, bytes, and unit price. All the data here that we're going to be working with inside of this script. 3,500 plus rows. Now, see, we did want to grab specific columns. That's where we can replace that asterisk with a column list, comma delimited. So here we're saying just give us the album and the genre columns from that view track details. If we hit execute, now we're just going to get those columns back. We're still working with every row because we didn't add a where clause to put filters, to put a filter or multiple filters on this query, but that's going to give us every single record and just those 2 columns. Now notice something here. Notice we've got a lot of duplicates in here because genre is stored at the track level and we're getting all of the tracks back. right, for every row in here. So it just hid the other columns that we didn't request, but we're still dealing with 3,500 plus rows. What if we just wanted the album listed once and the genre it was associated with? That's where distinct comes into play. So select distinct means just give us unique rows based on the result set that is coming back. So if we'd execute here, now we're only going to get that information listed once, and we're down to 360 rows, one row for each album, as well as the genre associated with it. Let's say that we wanted to add a sort to this. Now, I'm just going to highlight this without the order by, just to show you that this data is all out of whack here, right? It's not in any specific order. It's in the order that the view returned it to us as, and I don't have any order bys inside of the view, so it's all over the place. So if we wanted to sort, we could say order by artist. Notice I'm not highlighting these other two. I'm ending it right here. So this will then sort it by artist. That looks good. But we can also do multiple levels of sort. We can say order by artist, and then within that, order by album, then order by track. So if we highlight all of this and hit execute, we're going to sort first by artist, then by album, and then by the track within that album. All right. So lots of different ways to do order bys. You can have many different levels here. And by default, your sort is ascending. If you wanted to do descending in any of these levels, you can put a DESC after the column name, right? So that will then do that. It'll order it by artist ascending, and then by album descending, as well as track descending. Another common thing to do is to use the top keyword to return the top X number of rows. Now, by itself, this isn't really anything special, right? If we were to execute a query like this, give us the top 25, these columns from this view, it's just going to give us the first 25 results that view gives back to us. There's no real context around that 25. But when combined with an order by, now you can start creating things like scoreboards and leaderboards, and hey, give me my top 10 salespeople for this month based on how much they've sold. Give me my top 100 products based on quantity sold, that kind of thing. And in this example here, we're saying give us the top 25 tracks by length. Because we're ordering by milliseconds descending, the first 25 that come back are going to be the biggest tracks in our track table, or in this case, our track detail view. And there it is. So Battlestar Galactica, there's this track is very long right here. It's that many milliseconds. But you can see these are the top 25, the longest 25 tracks out of all 3,500 plus tracks inside of that view. Oh, you can also do percent, by the way. Rather than just give me the top 25 rows, give me the top 25% of rows. Now, instead of 25, we're going to get 876, which is 25% of the 3,500 records coming back from that view. Moving on, another very common thing you'll be doing in writing SQL is adding filters to your queries to filter for or to filter out specific data. So in this case, we're going to write a query that says, give us everything from that track details view where the genre is equal to classical. So only give us tracks that have classical as their genre. And if we execute this, we should see that there are 74 records returned, and only tracks that have classical as the genre were returned. So where clause, just simply how we write our filters. And the basic syntax is where column, operator, expression. In this case, our expression is just a hard-coded value, and our operator is an equal sign. And this whole thing is called a condition. And this is why we've got a nugget dedicated to enhancing your queries with conditions, because I've written some and seen some pretty ridiculous where clauses, because that's how you're going to slice and dice to get the exact data that you're looking for. That's where we'll talk about all the different operators you can work with. We've got arithmetic operators for addition, subtraction, multiplication, and division, and beyond that. We've got comparison operators like we have here, equals, greater than, less than equal to, greater than equal to. We have logical operators, your ands and your ors, and in fact, that's how you're going to create multiple conditions. So we could do or genre equals rock. And now we have two conditions, right? This is going to now pull back any track that has classical or rock as their genre. And if we execute that, now we're up to 1,371 rows with a mix of tracks spanning both of those genres. So check out enhancing queries with conditions to see all the cool things we can do with the where clause. Moving on here, I just wanted to throw you a couple of really interesting queries here. We're going to switch to our test database, which has our employee and employee detail table and department table inside of it. Here we go. So department, employee, employee detail. Let's say that we wanted to get a listing of employees who were hired in the last year. And here's where we're using an operator, a comparison operator that says give us all the employees where their hire date is greater than or equal to right now minus 1 year. So what this is going to do is this is going to evaluate to 1 year ago today. And you can actually test this out by putting a select in front of it. And let's just highlight this. I'll show you what 1 year is from right now was right there. 4/19/2015. It's 4/19/2016 right now. So let's take that off of there. So that's going to evaluate to 1 year ago. And we're saying give us all the employees where the hire date is greater than or equal to that date. So this will give us all the employees that were hired in the last year. And we can verify that by looking at their hire date. And we can see those are all greater than 5/19/2015. Just wanted to show you that you can start getting really crazy by adding functions into your where clauses to really create some dynamic queries. Here's another one. This one is the same as above, except we have multiple conditions. And instead of an or, like we did above here with our genre, we have an and. So this means give me only employees that were hired in the last year and belong to this department. This is the sales department, by the way. And we can also modify this. Instead of doing the last year, let's do the last, how about the last 6 months? So we'll change our interval here to month, and we'll change this to 6. So the last 6 months, and we're passing in get date here, which is the current date. So 6 months ago from right now in the sales department, how many people were hired? Just one. Old Joseph Dunn there. All right, let's move on to aggregating data with group by. So the group by clause allows us to roll up data with common values so we can run aggregates on that rolled up data. So in this particular example, we are grouping by the album column, which means it's going to take all the data with the same values and roll them up into one, which will give us access to running aggregates within those groupings. So here's group 1 and here's group 2. And here's the results, by the way, from executing that query. Because all this data is rolled up, by doing a count, it's just going to give us a count within each grouping. So this will be 10 and this will be 8. And then we're going to run a sum on unit price, which will add up all of the values in each grouping. Grouping 1 here will result to 990 and grouping 2, 792. Back in the Virtual Nugget Lab, let's take a look at a couple of simple examples. So I opened up our groupby.sql script here, which just contains a couple of queries. The first one is just showing you what the base data looks like. So all 3,503 rows out of our view. But what if we wanted to get a count? Maybe we wanted the top 10 albums with the most tracks. What albums have the most tracks inside of this view? Well, what we could do here is say select top 10 album as well as a count. And since we're grouping by album here, count will just automatically give us a count within each group. We're going to grab this from our view, we're going to group by album, and then we're going to order by the number of tracks. Notice that we're referencing our aggregated column here. And we're ordering it descending, so that's automatically, without the top 10, just going to give us a huge list of every album inside of the database ordered by the number of tracks. But if we wanted to cut out all the other stuff, maybe we just cared about the top 100 or the top 25 or whatever, we could just toss in that top. Let's do top 50. Here we go, top 50 albums with the most tracks. And there they are. Number 1 being 57, our last one being 16. Another simple example here. Now we're going to add another aggregate into the mix here. We're going to add a column called total cost, which is going to sum up the unit price, and since we're grouping by album, this is going to give us the total cost of an album. Remember, everything's done at the track level here, right? So if we just execute our first query here, every track has a price associated with it. So what this will do is give us the total cost of an album by summing up all of the track's unit prices within that album. In fact, let's add an order by to this. Let's order by, how about the total cost? And let's do that descending, so that way we can see the most expensive albums. So if we execute this, here we go, we see greatest hits. It's got 57 tracks, so obviously that's going to cost quite a bit. But there they are. Now our final example is just like our previous example, except that we've added a having clause into the mix. Having allows us to put filters on our rolled up or our aggregated data. So it works specifically with group by. You can't have a having without having a group by, and it happens after the aggregations occur. So in this case, we're saying give us all of the albums where the total of all of their tracks' unit price is greater than or equal to 8. And we can also add a where clause in here. In fact, let's do this. Let's add a where clause for a genre again here. Let's add rock since that's the most data. And now, where is a filter on top of the raw data? Having is a filter on top of that aggregated data. And here is the result. Check it out. So these are just all rock albums where the total cost is greater than or equal to 8. So anything underneath that didn't come back. And by the way, when you're testing this stuff, you can easily comment out specific clauses. So let's say, we want to test that without that where clause. we should get a lot more data. We have 89 rows here, so now it's going to include all the genres, and now we're up to 226 rows. You can see we've got scores from television shows and all that in here now as well. By the way, that's a very common thing to do when you're troubleshooting complex queries with complex where clauses, is to comment out specific conditions, look at the results, rinse and repeat until you find out where that problem is. Let's move on and talk about the different joins we have out there and the many ways that we can combine data from multiple tables. So joining allows us to combine multiple tables to make it look like it's one table. Anytime we join, we get access to columns from multiple tables, as well as the ability to write filters against both of those tables. And now, you may have a query that joins 20 tables together, but a single join operation itself always operates on two tables. You have a left table and a right table. And you can see we have all the possible combinations for combining data from multiple tables. And the most popular of those, and the one you'll be working with 90% of the time, is the inner join. So an inner join looks like this. We're joining two tables together on a common column. In this case, our left table has employee ID and our right table has employee ID. So what it's going to do is it's going to bring those tables together and only return the rows where we have those common columns. So in this case, it would return 5 rows because all of the rows in each of these tables match. That's called an inner join. Give me the data from both tables where that common column has a match in both tables. Let me give you an example of an inner join. So I opened up our join.sql script here and switched to our test DB, which contains our employee and our employee detail table. Here are those base tables for reference. I'm going to execute both of these SQL statements at the same time, which is going to give us two result sets. Here's our first result set, which is our employee table. There's 250 rows in this table. And if we head down to our employee detail table, this also has 250 rows. And because of referential integrity, we've got a perfect one-to-one match between both of these tables. So now we can write a query that says give us the first, last name, and hire date out of our employee table, the phone number, mobile number, and email out of our employee detail table. Here's our left table, employee. We're going to join our employee detail, which is going to be our right table, and we're going to join on that common column between those tables, which is employee ID. So if we highlight this and we hit execute, there's the results. 250 total rows with columns from both of those tables. Let's take a look at our left join. So a left join looks something like this, visually. What we're saying is give me everything from the left table, even if there's no match for it in the right table. And what it'll do then is null out any columns for that record inside of the right table. For instance, let's say that we had record number 6 over here in our left table, but we did not have a matching record number 6 over here in the right table. A left join will still return that record, where an inner join would have omitted that record from the results. And then in this case of a left join, anything in the right table, like phone number and mobile number, would just be nulled out. Now our left excluding join looks something like this. What this says is only give me the records that don't have a match in that right table. And we do this by putting a where clause to say where the key in our right-hand table is null. Let's take a look at this in the virtual Nugget Lab. Now, in order to show you how a left join works, we're going to need to add data into the employee table, add a record in there, but not add a matching record in the employee detail table. But because we designed this database with referential integrity all over the place, that wouldn't be possible. So we're first going to need to disable any sort of constraints on that table, specifically our foreign key constraint. There we go. So we turn that off. Now we should be able to get a record in here. I'll add a record for me inside of the employee table. Perfect. There it is. And now I can show you how left joins work. So let's start with the basic left join. And this is the same exact query as above. The difference is we're pulling back a couple of different columns, but also we're doing a left join rather than a regular join. And you can, by the way, specify inner join, but join by itself will default to an inner join. So what we're saying here is give us everything from the left-hand table, hence the left join, even if there isn't a match in the right-hand table. And we know there isn't for this record that we just put in here. And what it'll do then is for all the right-hand columns, which are phone number, mobile number, and city, it will null them out. So let's hit execute. Let's see what we got. Let's scroll all the way down to the bottom, and there is our brand new record. Here's our left table and the columns from it. Here's our right table, all nulled out. So again, if this was an inner join, what would happen? We wouldn't see this record. In fact, let's test that. Let's just run our first query here, which is an inner join, and that record, 251 there, Darth Vader, that's me, it was totally omitted from the results. Now let's add on to that a where clause so we can see what a left excluding join looks like. And this is how we can identify records that don't have a match, because we're going to put a where clause that says only give us back records where the employee ID in our right table is null. So let's add that into our query here, and let's execute it. And now we're only going to get that record back. That's a left excluding join, because it helps us identify what records exist in the left table but do not exist in the right-hand table. Back to the drawing board here. Let's take a look at the right join and the right excluding join. Now, these are just the exact opposite of the left join. So if we do a right join, it's going to give us all the rows of the right-hand table, and then anything that doesn't have a match in your left-hand table, those fields will get nulled out. And a right excluding join then is just like a left excluding join. It'll allow us to identify those records that do not have a match in the left table. And yes, these are interchangeable. It all depends on how you design your queries. It all depends on what you put as your left-hand table and what you put as your right-hand table. Here's an example in the Virtual Nugget Lab. This time, we're going to need to add an employee detail record without a matching employee record. So we're going to do the same thing here. We're going to disable constraints on our employee detail table, and then we're going to add an employee detail record that doesn't have a match in the employee table. There we go. And now this is, again, the same exact query. The difference, though, is we're doing a right join saying that we want to grab everything, even if it doesn't have a match in the left table, the employee table, inside of the employee detail table. So if we execute this, now, if we scroll down, here it is. Here is that record. It just nulled out the fields in the left-hand table that didn't have a match. And now the right excluding join will do the same thing. Now we're going to write a little where clause to say where the employee ID in the left-hand table is null, and that will allow us to identify just that record. Finally, we have outer joins. And an outer join is basically the combination of both a left and a right join. It's going to return all the records from the left, even if they don't have a match in the right, and all the records in the right, even if they don't have a match in the left. And for those that don't have a match, it'll null out those fields accordingly in the opposite table. And then an outer excluding join allows us to, again, discover those records on both sides and will not return any of the matching records. Now, we shouldn't have to do anything special to see this in action, because we already put data in our employee table that doesn't have a match in our employee detail, and vice versa. So if we run this without our exclusion here, just changing right join and left join to full outer join, we should get all of our matching records as well as our unmatched records on the left side and our unmatched record on the right side. And the inclusion piece then just combines both the left and the right as well, because we check for is null on the left-hand side of the join on the key as well as the right-hand side of the join on the key across both tables. And now we should just get those two records. Perfect. So those are all the different ways that we can join data together. And again, the most common by far is going to be your inner join. It's going to be special circumstances where you use left and right and outer joins. But on databases where referential integrity, isn't a thing or was added later, you'll certainly have discrepancies in data, and these will be very, very handy tools in identifying them. Let's finish up with a look at our view one more time here. So this should start to make a little more sense, right? Here we have a lot of joins, but every single join operation just works with two tables. So here we're joining artist to album on the artist ID column between these two tables. Then we're joining track to album on the album ID. Then we're joining genre to track, and then we're joining media type also to track. So you can have many tables all joined to one table, but you're going to do them individually with its own join operation. In this CBT Nugget, we saw how to write basic queries. We got familiar once again with the basics of select, how to pull columns from a table or view. We saw how to sort those results using order by, how to filter using where, how to aggregate using group by, and took a big look at the many ways that we can join multiple tables together. I hope this has been informative for you, and I'd like to thank you for viewing.